Let's discuss Unit 5, 2026 January paper. So in this paper, I'm going to discuss it in 4 parts. The reason is then I have more time to explain the content of the theory. Let's take question number 1. A student wanted to measure the standard electrode potential of a half cell for the reaction shown using a standard hydrogen electrode. So when you're trying to find the electrode potential, standard electrode potential. So this is the setup you need. First, you have to make a setup of the electrode that you want to measure. So this is the electrode potential of this one. I have to measure it. Let's see how I'm going to create this electrode. So to create this electrode, so I have to do this measurement at temperature of 298 Kelvin, or we call it 225 degrees Celsius. So 298 Kelvin or 25 degrees Celsius. So what I have here is I have vanadium 3 plus ion aqueous, vanadium 2 plus ion aqueous. I don't have a metal plate in this equation. So if you don't see a metal in the equation, you have to use a supportive electrode. The supportive electrode that we use in our electrochemistry is platinum. To create an electrode, we use platinum as supportive electrode if you don't see any metal in your equation. So I have platinum. So inside this platinum is immersed in an aqueous solution. What should we have in that aqueous solution? We have to have these two ions, vanadium 3 plus ion and vanadium 2 plus ion. So I need to have a solution of vanadium 3 plus. The concentration should be 1 mole per cubic decimeter, and solution of vanadium 2 plus, the concentration of that should be also 1 mole per cubic decimeter. Okay. Then I should connect this electrode through a voltmeter to standard hydrogen electrode. What is standard hydrogen electrode? Again, in standard hydrogen electrode, we take this equation. We always try the equation towards a reduction direction. So we have H plus ion becoming hydrogen gas. H plus aqueous. Right. So to become hydrogen gas, you need to take 2 electrons. 2 H plus ions take 2 electrons, becoming hydrogen gas. So I'm going to make this electrode. Again, you can see that there's no electrode there. So we don't have electrode there. So therefore what we have to do is we have to use, like as previous case, we have to use platinum as the supportive electrode. So I have to have platinum here. All right. So I have platinum here, and I have to have H plus ion in the aqueous solution. So I have to have H plus ion aqueous solution. We know the concentration 1 mole per cubic decimeter. And now here we have a gas. Hydrogen is a gas. So I have to pass hydrogen gas into this platinum plate. For that I use a glass cover like this. And from this delivery tube, I'm going to send the hydrogen gas. So I'm going to pump hydrogen gas in from here. And its pressure should be 1 atm. 1 atm, or you can call it 100 kilopascal. It's the same, right? 1 atm is same as 100 kilopascals. Okay, 1 atmospheric pressure or 100 kilopascal. So this is the setup, and to complete this setup, complete the circuit, I have to have a salt bridge here. Okay, so this is the setup that I'm going to use. In this setup, I'm going to measure the standard electrode potential of vanadium 3 plus, vanadium 2 plus electrode. This electrode we have given here in this equation. Let's see which could not be used in making this measurement. An electrode of vanadium metal, which could not be used in this making this measurement. You can see that the electrode we have to use here is platinum. It's not vanadium. So we found the answer. Answer of question number 1 is A, but anyway, we'll read the other answers also. Pressure of 100 kilopascal. 100 kilopascal means kilo means multiplied by 1000, no? So that means you are talking about 100,000 pascal. Yes, roughly 1 ATM is equal to 100,000 pascal. Almost. Okay. So that's correct. Because they're asking more suitable. It's not exactly 100,000 pascals, but it's very close to 100,000 pascals. A solution of vanadium chloride, concentration of 121 gram cubic deciliter. Solution of vanadium 2 chloride. They say that take vanadium 2 chloride, that means VCl2. So I think from this VCl2 we can get vanadium 2 plus. How much of it? In 1 cubic decimeter, okay, they say that 1 cubic decimeter is there. How many grams we have? 121.9 grams. 120.9 grams, that's the molar weight of vanadium 2 chloride also. So we know a number of moles equals mass divided by molar mass. Mass we have is 121.9 grams in 1 cubic decimeter. Molar mass also 121.9 grams per mole. So that means 121.9 grams means 1 mole. 1 mole in 1 cubic decimeter. That's the concentration we need. 1 mole per cubic decimeter. Yes, that's a correct answer. A temperature of 298 Kelvin. Yes, that should be the standard temperature. So answer for question number 1 is A. Right. Let's move on to question number 2. An electrochemical cell was set up as shown. Okay, so we have copper metal and silver metal. What is the EMF of this cell? The equation for EMF, I'll just remind you, EMF equation is EMF electromotive force, or we call it E cell value. We call it EMF or E cell value equals electrode potential of cathode plus electrode potential of anode. This is the equation that most of the textbook you can find here. But what I'm going to do here is I'm not going to use this equation. I'm going to change this equation. I'll tell you why I'm changing this equation. So when I'm going to find E cell value, because most of the students, they will mixed up when they use this equation. So E cell value equals, this is the equation I'm going to use, E cathode minus E anode. You might be thinking, what? Minus? Let's see how it works, right? So simply what you have to do is, first, when you see these electrodes, I can see copper metal here and copper 2 plus ion here. Let's find the reaction where you see copper and copper 2 plus ion. Copper and copper 2 plus ion. I can see it here in this number 14. Yes. Then we find the equation where we have silver and silver nitrate solution. That means silver and silver plus ion. Okay, silver and silver plus ion. Silver and silver plus ion are here. Equation 22. So what we should do is, now it says key cathode minus E anode. This is the way of identify the cathode. What you have to do is a greater value. The big value is the cathode. So big number. So big value. So what means you have plus 0.35 and plus 0.80. So you know that downward the values are increasing. So down, the one which is in the bottom is the cathode. So big value is silver plus ion becoming silver is plus 0.8. I said big value is the cathode. Okay, let's put the big value as our cathode. Okay. So therefore E cell value equals plus 0.80 minus anode is the smaller value plus 0.34 plus 0.80 minus 0.34 is plus 0.46. Therefore answer for question number 2 is B. Now you might ask, why didn't you use that first way, that means this equation? I'll tell you, if you use that equation, it will be a 2. Now it's so simple, no? E cell value is E cathode minus E anode. Cathode is a big value. If it is a functioning cell, yes, it's a big value. You put the big value there and minus anode, the small value. Let's see what will happen if you use the equation that which you can find in most of the textbooks. Okay, so if you find it in most of the textbooks, this equation, this is the process that you have to follow. Okay, so EMF value is there. So both are, can you see in, now we found the equations and their electrode potential. Can you see both equations are given in a reduction way? Copper 2 plus ion takes 2 electrons becoming copper. Silver plus ion takes 1 electron becoming silver. But we know that you can't have two reactions. So you have to identify which one is reduction, which one is oxidation. You can't have two reduction reactions or two oxidation reactions in a normal electrochemical cell. But there are some reactions which can perform. But even though if there's oxidation, there will be a reduction part. So we have only two equations. If one is oxidation, other one has to be a reduction. And we know that one which has large electrode potential is the cathode. Cathode is the place where reduction takes place. So I have to write the reduction reaction. So this is the reduction reaction. So reduction reaction is, so simply silver plus ion takes 1 electron becoming silver. What is the electrode potential value? Plus 0.80. Then if this is reduction, other one has to be oxidation. So that means the way I have written is wrong. So I have to reverse the reaction. It should be copper becomes copper 2 plus iron plus 2 electrons. So what I did was I did drove the reaction backward. So since I did the reaction backward, so the value will change. It won't be plus 0.34. It will be minus 0.34. Now they say that EMF value equals E cathode minus E anode. Cathode is where reduction takes place. It is plus 0.80 plus E cathode plus E anode. So E anode is the oxidation reaction. Now we change the sign. Why is that? Because the equation reversed. So it is minus 0.34. Can you see? It's the same answer, but you have to do a lot of work. You have to identify which one is the anode, which one is a cathode, and you have to reverse the reaction of anode, and therefore you have to change the sign of this one. But if you remember my equation, it's cathode minus E anode. Why did I put a minus sign here? Whatever you put in the anode value, it will reverse automatically by the equation. So that's why I use that equation. Then you have less work and you have less to think when you are doing the calculations. So answer for question number 2 is B. Right. Let's go for question number 3. So question number 3 has two parts. Yes. The concentration of an iodine solution was determined using a standard solution of sodium thiosulfate. So we have iodine solution. We have determined using standard solution of sodium thiosulfate. They say that 4.17 gram of sodium thiosulfate was dissolved in a deionized water. Okay, so we have 4.17 grams of sodium thiosulfate Na2S2O3 was dissolved in a deionized water. So we dissolve this one in water, right? The solution made up to 250 cubic centimeter volumetric flask. So we dilute this solution up to 250 cubic centimeters of solution. Okay, we are going to dilute it up to 250 cubic centimeters of solution. Now I have sodium thiosulfate solution in a volumetric flask and mixed 25 cubic centimeters of portion was transferred into a conical flask using a pipette. Okay, from this main solution I took 25 cubic centimeters. So I took 25 cubic centimeters into a conical flask. Now in this 25 cubic centimeters I have sodium sulfate Na2S2O3. Okay. The measurement uncertainty of the volumetric flask. Okay, volumetric flask is this one. So measurement uncertainty of the volumetric flask was plus or minus 0.30 cubic centimeters. The measurement uncertainty of the pipette was plus or minus 0.03 cubic centimeters. The total measurement uncertainty of the balance weight, the mass of the sodium thiosulfate is plus or minus 0.01 grams. Which is the correct for the percentage uncertainty for this experiment? Okay. So let's see how we can find the percentage uncertainty. So first I'll find the percentage uncertainty for the balance. The equation for percentage uncertainty is uncertainties equals, what you do is you take the error. So there's a measurement uncertainty, or we call it error. Okay, the error, what we do is we take the error, or we call it the measurement uncertainty, divide by the reading, whatever the reading you took, and you multiply it by the 100. Okay, let's find the percentage uncertainty of the balance. How to find percentage uncertainty of the balance? You take the reading and the error. So error for the balance is plus or minus 0.01 grams. Divide by the reading that you measured is 4.17 into 100. Okay, you found the percentage uncertainty of the balance. Then we have to find the percentage uncertainty of the volumetric flux. Percentage uncertainty of the volumetric flux, again you take the error. Volumetric flux is 0.3, divide by the reading you took is, you volume you measured is 250 into 100. You find the percentage uncertainty of the volumetric flux. Then percentage uncertainty of the pipette. You transfer this liquid into this conical flask using a pipette. So if you want to find the percentage uncertainty of the pipette, again what you do is you take the reading, error first 0.03, divide by the reading you took is 25 into 100. Okay, you find percentage uncertainty of the balance, volumetric flask, and the pipette. The balance, pipette, and volumetric flask has the same percentage uncertainties. Obviously, you know that these two, the volumetric flask and pipette, looks okay, but if you take this balance, we know that completely number has to be a different one. Anyway, I'll just do the calculation and just see two of them. So we'll do it for, yes, when I do the math, they will get two different values. You can simply divide these two numbers. What you can do is you divide 0.01 by 4.17 and 0.3 by 250. So you can see that they are two different values. Since they are two different values, the balance, pipette, and volumetric flask have the same percentage uncertainty. It's incorrect, because when you put them into math, calculate it, they are not equal. The balance percentage uncertainty is the smallest. The balance percentage uncertainty is the smallest. Okay, let's see that one also. Okay, so if you go for the balance percentage uncertainty, right, if you do the calculation, so we have 0.01 divided by 4.17, 0.01 divided by 4.17, so that value is 2.398 in 10 to the power minus 3. You multiply that by 100. So when you multiply it by 100, you get the value as 0.23. So percentage uncertainty for the balance is very close to 0.23. We don't need the exact value, just need to get an idea. So it's 0.23 as a percentage. So we'll take 0.3 divided by 250. So we'll take the other one. So we have 0.3 divided by 250 and multiplied by 100. So if you multiply by 100, so you get the answer 0.12. Okay, so obviously this is 0.12. So if you do this value, it is 0.12%. So we can't use that word. This is the smallest one. The balance percentage answer is the smallest. That's also wrong. So second one is also wrong. The pipette and volumetric flask have the same percentage uncertainty. I think it looks fine, yeah, because I'll show you this one. Because if you take 0.3, if you take the percentage uncertainty, which is 0.3 divided by 250 multiplied by 100, and here 0.03 divided by 25 multiplied by 100, and if you do the math, yes, both have 0.12% as the percentage uncertainty. Yes, that's the answer. So answer for question number 3, part A is C. The volumetric flask percentage uncertainty is 10 times that of the pipette. No, they have the same percentage uncertainty. So therefore that's also incorrect. So answer for question number 3A, part A is C. Okay, let's go for question number 3, part B. Right, question number 3, part B. The 25 cubic centimeters of sodium thiosulfate solution in the conical flask was titrated with the solution containing iodine in the burette. No indicator was used. We know that indicator for this titration is starch. They have not used this indicator. What is the color of the solution at the conical flask at the endpoint? So we know the equation. Let's try to memorize it. So we have iodine reacts with sodium thiosulfate, 2Na2. We need 2 sodium thiosulfate, Na2S2O3 gives you 2 sodium iodide plus Na2S4O6. We know that iodine is a yellow color solution. If the concentration is really high, it might be a little bit brownish. And when it becomes sodium iodide and sodium Na2S4O6, both of them are colorless. So that means our color will change from yellow to colorless. The endpoint color change is colorless because we are not using an indicator. No, it's not the answer. It's wrong. Because reason is, this is what we used to learn, right? But here see, 25 kb sodium thiosulfate solution is in the conical flask. Our sodium thiosulfate is not in the burette. All this time when you are learning in our classroom, in our classrooms, we learned that sodium thiosulfate was in the burette. And what was in the conical flask is iodine. But here, sodium thiosulfate is in the conical flask. To that, we are adding iodine from the burette. Iodine is in the burette. They are asking what can you see in the conical flask. So sodium thiosulfate is colorless. So when I add iodine, when I add the first drop of iodine, yellow drops turns to colorless. Second drop of iodine, yellow drops turns to colorless. So this will keep on happening until there are sodium thiosulfate in the solution. Yellow color turns into colorless. But there will be one point, there are no more sodium thiosulfate. Sodium thiosulfate. I was telling something else. Yeah, there are no more sodium thiosulfate. You don't have sodium thiosulfate anymore in the solution. When there are no more sodium thiosulfate in this, like in this conical flask, the next drop of iodine that you have added, there's nobody to react with iodine. So that's, as a result of that, what will happen? Iodine has a yellow color. That yellowishness will spread throughout the conical flask. Then only you know that that's the end point of the titration, because there are no more sodium thiosulfate to react with this iodine. So at the end point, what is the color you are going to see is a yellowishness, because we are adding iodine to a solution where there are no sodium thiosulfate left. So therefore, at the end point of the titration, what we are going to observe is very pale yellow. So therefore, my answer for question number 3B is C. Right. Let's go for question number 4. What is the electronic structure of the metal ion in double salt? Okay, we have, so there's double salt. What is the formula? NH4 twice. We know that NH4 twice. NH4 plus sign is +1. NH4 is +1. So this is +2. SO4. We know that SO4 is 2 minus sign. SO4 sulfate ion is 2 minus sign. So it's -2. So it's neutralized. We don't need to worry about them. Then Fe SO4.6H2O. We know that water is a neutral molecule, so there's no charge on them. So we can remove that. So SO4 is 2 minus. If SO4 is 2 minus, ion has to be +2. So they are talking about Fe2 plus sign. Let's try the electron configuration of ion. Wait, scandium, titanium, vanadium, chromium, manganese, ion. So it's 26. 26 means 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now we have 10, another 10 electrons, so we need 6 more, 3d6. And we know that when you are removing electron, we remove the electron first from the 4s subshell. So it's iron. So when it becomes Fe2 plus iron, it will have only 224 electrons. What will happen here is the outermost 2 electrons will get removed. So that means these 2 electrons. So therefore, what will be the electron configuration? It will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s is now 0. Therefore 3d6. So we are searching for electron configuration of 3d6, and there's only one answer with 3d6 electron configuration. So therefore answer for question number 4 is C. Okay, what we did was we finished the first 5 MCQ in the unit 5 paper. So the next 5 I'm going to release another video, because I'm going to do this 5 by 5, then I can discuss more theory part by spending more time. And also we were discussing about what are the exercises that you can do to emphasize or like increase the efficiency of your brain, because those are called neurogenesis exercises. In unit 4 paper, when you are discussing, we discuss 4 exercises. So I'm going to add 5 more exercises into that list. So I just go through them really fast. First exercise that you can do is routine reversal. Routine reversal means, let's assume the things that you used to do. Let's take early in the morning, we wake up, you're going to have the breakfast, then you're going to get ready for the school. But we can change this pattern. For like, let's assume now, from today onward, what you're going to do is, you're going to get fully dressed, and then you're going to have your breakfast. So what you do is, you just flip, that means you just change your routine. So when you change the routines, always your brain has to do some work. It helps you to like activate your neurons and also neurogenesis, and also improve the neuroplasticity. Another exercise that you can do is pathfinding variation. Always when you're traveling, you know that if you're going from one place to another place, there's a usual route that you follow, right? But there are optional routes also. You can use those routes. Or if you used to ride bicycle, you can try new routes, because you know that if you take this narrow like routes, what will happen, no matter where you end goes, it will end up somewhere like very close by. So there are linking roads you can find there. So if you don't have bicycle, if you can't do this one, what you can do is, when we go to a supermarket, we usually start shopping from, there's a certain corner. We start from one corner and you go to the end of the supermarket. What can you do is, as soon as you enter, you go to the place where you're going to end the shopping, and you start from there and you come in the reverse direction. That's another thing what you can do. That means pathfinding variations. Another thing that you can do is like try a new food, new taste. So these type of, when you try new food at least once a week, that's also help for this neurogenesis. Next one is perspective shifts. Let's see what is the meaning of this one. Now let's assume you used to go to school in a tram or bus or a car. For one day you just change. You might order a tuk-tuk, or you can go in a train, or sometimes you can at least, like let's take in the car, if you are used to sit the front seat next to the driver, you can go to the back and ask from one from the back, come in the front seat. Change your place at least, and you can observe the surroundings in a different way. That's also like good exercise for your brain. Then the last one is, there are more, I'll bring them in the next videos, environmental refresh. So that means in your house, even in your table, there are ways that you use to keep your stuff. So what you have to do is always change, even at least add a flower, like flower flask, or something, like even the place where you used to sit, the place of the position of your chair, everything, just change something. So rearrange the furniture. So when you rearrange the furniture, always your brain has new tasks to do. So this will improve the neurogenesis and your cognitive skills. Right, so those are the exercises that you can follow, and I'll come up with the second part of this unit 5 video. So if you have any doubts, what you have simply do is just type a comment, then I go through it. I can make videos for a specific subject part. If you want to learn about electrochemistry, just simply leave a message, then I make a video on electrochemistry and I'll upload. Okay, see you all with the part 2 of unit 5 paper by tomorrow. Okay, thank you.